and positive values are passed. So applying ReLU to this is a feature map here. So imagine we've come from input image here. Let's imagine it's on the left here. We applied a kernel and we got this feature map out of it. We haven't applied ReLU just yet. So now applying ReLU, this -5 here, and -1 all become 0. So this is what ReLU does to our feature maps. So how does this actually look in an image? This is an example of actually taken from here, that if we have a feature map that looks like this, with black being negative and white being positive, and you only pass the non-negative values, this is what it becomes. So you can see it still preserves a lot of information in this image here, without maybe some of the noise that is seen here. So this is what ReLU actually does. So now let's move on to section 7.5, which is pooling. Hi, and welcome back to 7.5, which is about pooling. This is the next sequence of layers in our CNN. So far, we've dealt with the convolution part and ReLU. Now let's look at pooling, or also known as subsampling. So pooling, as I just said, is also known as subsampling or downsampling, is a simple process where we reduce the size or dimensionality of the feature map. The purpose of this reduction is to reduce the number of parameters that we need to train whilst retaining most of the important features and information in the image. There are basically 3 types of pooling we can apply. There are actually some more, but let's take a look at these 3 main types that are used. So here's an example of max pooling. Imagine this is the ReLU output from this output here was produced from the ReLU layer. So you can imagine these values, these zeros here, were actually negative values. So max pool basically uses a 2x2 kernel here. We can define this kernel size to anything we want, just like we did with the stride of the kernels we used in the convolutional layer. And basically, using a 2x2, it splits this up into 2x2, 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 2x2 grid. So what it does, max pooling, takes a max value out of each, 234, 167, 241, and 235, and puts them into this block here. So this is what we call downsampling or subsampling. Basically, we've sort of like compressed the image here and retained the most max important features. Actually, let's go back to the previous slide and the previous slide. We mentioned average and sum pooling. Now, as you can imagine, average and sum pooling would just simply be the average of these values here, here, or here, or here, and sum pooling would just be the sum of these values here. So that's also a way we can use pooling. However, in majority of convolutional neural nets, we always use max pooling. So this is our layers so far. Just to do a recap, we have our input image with our kernel that is being slid across this image, producing multiple different filters here, all of which are the same size as the input image, and that's because of 0 padding. Then we have a ReLU output, which basically is the same size output matrix as this, except all the negative values turn to zeros. And then we have the subsampling or pooling layer, or downsampling, which basically reduces this image, this matrix by half, 14 by 14. Because as you can see, using a 2x2, we had a 4x4, now we get a 2x2. And that's this here, still 12 filters, however, they've now been downsampled. So let's move on now. So let's talk a bit more about pooling. Typically, pooling is done using 2x2 windows with a stride of 2 and no padding applied. That's how we actually get this 4x4 here. It takes a 2x2 jump, 2x2 jump, and blah, blah, blah. So for smaller input images or larger images, we can use larger pools or smaller pools, whichever you want to do. And using the above settings, pooling has the effect of reducing dimensionality. Width and height, those are the only 2 dimensions we reduce here, of the previous layer by half, and thus removing 3/4 or 75% of the activation seen in the previous layer. So let's keep moving on. This makes our model more invariant to small or minor transformations or distortions in our input image, since we're now averaging or taking the max output from a small area of an image. What this actually means here is that we're, instead of like looking at specific pixels here in an image, because we're actually doing downsample and looking at the max in an area, we sort of add some sort of invariance or spatial invariance to our filters here. So our filters aren't super specific to certain areas. And remember, they're being slid across the image. So imagine this filter has been slid across the image looking for a specific edge or whatever. It can actually add some invariance now to it. So this actually increases basically the ability of our convolutional model to generalize to information it's never seen before. So now let's move on to what is kind of the final layer. There are some layers in between. I will discuss them later on. But for now, this is the core of the CNN, and this is the last layer, the fully connected or FC layer. Hi, and welcome to chapter 7.6, where I discuss the fully connected layer, and I tell you why it's so important. So the fully connected layer, or FC layer, and it's also called the dense layer in Keras especially, but in a number of documentation and other tutorials, they call it the dense layer too. So previously we saw in our neural net that all layers were fully connected, okay? Now what does fully connected mean? Fully connected means that all nodes in one layer are connected to the outputs of the next layer. Now that doesn't happen in basically throughout the CNN except at the fully connected stage. So the fully connected stage here, basically it's a layer right here that takes the outputs of the pooling layer and then passes it to the fully connected layer here, which then outputs the class probabilities here. So the FC layer outputs these class probabilities, and each one is a probability corresponding to a class. So as you can see, panda, cat, dog. This is clearly a cat. So it does this by using the softmax function. So going back to it here, the FC layer outputs stuff here that goes into a softmax function. And the softmax function basically is what gives it its probabilities, because it must sum to 1, and that's exactly what a softmax function does. Okay, we'll take a look at it here. So by the way, a softmax function is actually an activation function as well. Just remember that. And it turns the outputs of the FC layer, the last layer, into probabilities. So let's say the output of the FC layer was 2, 1, 1. Applying the softmax squashes these real value numbers into probabilities that sum to 1. So the output would now be 0.7, 0.2, and 0.1. So now that we've discussed all the building blocks of the CNN, which if we were to go it over now, it would be the convolutional kernel, it would be the ReLU, the pooling, and the fully connected layer with the softmax at the end. So how do we actually train CNNs? We're now about to move on to that section, which is 7.7. Okay, so we've just discussed all the layers that comprise of a basic CNN. So now let's talk about how we actually train our CNNs. So CNNs are basically a type of neural net, and they lend themselves perfectly to image classification. It basically learns spatial image features, but because of the max pooling and multiple filters, it is basically somewhat scale and distortion invariant. So this is an illustration of the feature maps that a CNN learns. Okay, it's taken from this link here. You can check it out. So essentially, you can see the beginning convolutional, or the early. This is input, and this is close to the output, or the output itself. So you can see the early filters learn basically simple, edge detectors or pattern recognizers. However, the mid-level features are a bit more abstract and a bit more complicated. You see these three weird lines here. Something that looks like an eyeball. I'm not even sure what it is. Could be a wheel, actually. And then, as we go further, the next layer of convolutional filters. Remember I said you can have multiple layers of them, like multiple sequences of convolutional layers? Well, this is exactly an illustration of that. And as you can see, the patterns get much more detailed. And basically, this is how neural nets, or CNNs I should say, this is how their filters actually learn, and this is what they pick up in images. Later on, in about 2 or 3 chapters from now, we're going to do some visualizations of our own. So basically, just a quick review of CNNs again. On our layers, convolution plus ReLU done here, then pooling, then we can do convolution and ReLU again, then more pooling, and then pass everything to the fully connected layer, which outputs our class probabilities. So how do we train CNNs? So just like in neural nets, training CNNs is essentially the same thing, okay? So we have a random weight initialization of the convolutional kernels. That's all our kernels we described before. They basically start with random values. Then we forward propagate an image, one sample image, through our network that goes through all these layers here. And we get the error being basically the class probabilities. So let's say we were looking for an output of 0.2, 0.4, 0.4. When the true probability is with this, basically in class probabilities, you want it to be as close to this as possible, where it's very sure it's in one category and very low probability in the other categories. So then we apply a loss function, pass it through an optimizer, and use backpropagation to update our gradients via gradient descent. And we keep doing this, we keep propagating all our images through our network till we complete an epoch, and then we keep completing epochs until our accuracy and loss are satisfactory. So now let's take a look at how we actually design our own CNNs. Okay, so welcome to chapter 7.8, where we talk about how we design our own CNNs and the layer patterns involved. So basically all basic CNNs, we're not talking about exotic CNNs here, which we will get exposed to later on, follow this sequence. You have an input, a convolution, ReLU applied to the convolution output, pooling applied to the ReLU output, pooling goes to the FC layer, and FC layer with softmax gives us the output. That's basically it. And basically when we talk about deep convolutional neural networks, we talk about multiple convolution ReLU pooling layers. So you can have sequences of 1, 2, 3, these 3 layers, over and over and over again, till we get to the FC layer. So here's the basic design rules, okay? Input layers typically are square. So with MNIST 28 by 28 or 64 by 64. Now this isn't necessary, but it simplifies our design and speeds up our matrix calculations. So if you have images of all different sizes, it will be best if you just resize them all to one standard size, okay? Input should be divisible by 4, which allows for downsampling. Okay, that's a max pool layer, in case you forgot, with a stride of 2. So we tend to keep these, basically these values here divisible by 4. Filters are typically small, either 3 by 3 or 5 by 5, but they can easily be 7 by 7 or 9 by 9, so don't let me stop you from trying those filter sizes. Stride is typically 1 or 2. I usually use stride of 1. However, if the inputs are large, you can get away with a stride of 2. Zero padding is usually always used so that our convolutional output layers are the same size as the input. And our max pool kernel is typically 2 by 2, which I said previously up here. And dropout, which we will discuss further, is a very, very useful technique and easy to apply to avoid overfitting in CNNs. So, part 2 of this slide. So the more hidden layers, the more features, okay? That makes sense because obviously each time you do a convolution, apply a convolution kernel, you're getting a bunch of filters, which obviously means more features. So we want, if our data set is complicated, we want to have maybe at least 2 or 3 sequences of convolutional layers. That means this here, these 2, ReLU, convolution, pooling, at least 3, maybe 2. And that way, this is the sequence here, input, conv, ReLU, pool, conv, ReLU, pool again. And basically this allows our filters to learn low-level features here, then mid-level or higher-level features here. So basically, this is some examples of CNNs we'll be actually building in our course. This is AlexNet, which is one of the early, most famous CNNs here. This is an example of how it's constructed. You can take a look of it here. The parameters they used. Stride of 4, interesting. So you can take a look. Alright, as you see here, there are actually 2 fully connected layers, and you can actually do that to basically, you can have consecutive dense layers of fully connected layers, and it doesn't even have to have the same number of values, okay? It's another one we'll be making in this course. We will be making it and using it, the pre-trained model. We aren't going to train VGG or VGG19. It is insanely parameter intensive, and basically, I mean like millions of parameters, and it takes a while to train. Okay, so now you're ready to actually start building convolutional neural nets in Keras. This is the exciting part of the course, and it's actually quite easy, so let's get down to it. Hi, and welcome to chapter 8, where we actually get to build a CNN in Keras. So this is going to be an exciting chapter, and here's what we're going to learn. Firstly, brief introduction to Keras and TensorFlow, what they are and how we use them. how we start building our handwriting recognition, basically our approach to this problem, how we load our data, how we get our data in the right shape or format for Keras, what is hot1 encoding, how we build and compile our model, how we train our classifier, how we plot our loss and accuracy charts that we've seen before, how we save and load our model, so after we train it, we can now save it and reuse it anytime we want, how to display basically our model visually, so it's like an architect blueprint of our model, and basically how we actually can now build another image classifier using the CIFAR10 dataset. So let's get started. Hi, so welcome back to chapter 8.1, where I introduce you to Keras and TensorFlow. So what exactly is Keras? I've mentioned it countless times on this course, but I haven't actually told you precisely what it is. So Keras is a high-level neural network API for Python, and it makes constructing neural networks, all types, not just CNNs, but all types of neural networks. It makes it extremely easy and extremely modular, just to add layers, swap in stuff, change different things, configure your loss functions, configure your different types of activation functions. It's quite nice. It has the ability to use TensorFlow, CNTK, which is used for natural language processing, and Theano, which I used to use quite a bit of Theano. However, I've now moved to TensorFlow and I haven't looked back. Not because Theano is bad. Theano just basically has stopped being updated now. Project is pretty much done and closed, and everyone is pretty much adopting TensorFlow now. And it was developed by Francois Cholet, and this has been a tremendous success in making deep learning much more accessible to the masses. So what is TensorFlow though? I said Keras used a TensorFlow backend, but what exactly is a backend? Okay, so TensorFlow is an open source library that was created by the Google Brain team in 2015. Probably was being used inside of Google internally for many years prior to 2015. And basically it's an extremely powerful, extremely efficient and fast machine learning framework that is used for high performance numerical computation across a variety of platforms such as CPUs, GPUs, and TPUs. These engineers, these guys at Google Brain, they developed this basically super fast library similar to NumPy, but basically incorporated it and built it around deep learning. So they have all these deep learning functions that are part of the TensorFlow framework. It too actually has a Python API, and it pretty much is accessible and easy to use, but Keras is much easier to use. So why use Keras instead of pure TensorFlow? As I said, Keras is extremely easy to use as it follows basically a Pythonic style of coding, and it is extremely modular. You don't even have to be a proficient programmer to use Keras. This modularity means that we can actually just start doing different things with our neural nets or CNNs. We can easily change cost functions, optimizers, initialization schemes, activation functions, try different regularization schemes, introduce more layers, reduce number of filters. All of those things are done super easily inside of Keras. So it allows us to build these powerful neural nets quickly and efficiently. And obviously it works in Python. And Python is one of my favorite, actually it is my favorite programming language ever, because it makes so many complicated things super easy. TensorFlow is definitely not as user-friendly and modular as Keras. I've used TensorFlow a bit, to be fair, but I was using Theano at that point, and Theano actually was quite hard, so TensorFlow seemed easy for me at that point. However, nothing beats Keras in terms of ease of use. So unless you're doing complicated models or academic research, or basically working for some sort of high-performance startup, you don't necessarily need to use pure TensorFlow for anything. So now you're ready to see some actual Keras code. Well, it's actually Python code, but we're using the Keras library. And this is how we actually construct and build models inside of Python. So firstly, we import the sequential model from Keras. Basically, the sequential model is the main type of model you'll be building in Keras. Basically, all the CNNs and neural nets I've shown you before were sequential models. If you're doing something exotic, then it will probably not be sequential, but that is rare and probably beyond the scope of this course right now. It's basically academic research. So let's move on. So we defined our model here, We initialize it by running this line here, sequential these two brackets. And then now let's add some convolutional layers to it. So before we do that, we have to import these layers from Keras here. So from Keras.layers, we import dense, dropout, flatten, conv2d, max pooling. Now I don't have dropout here, but it's being used in the model we actually are going to code. So I left it in just so you guys know how it's referred to here. Okay. So firstly, model.add. We're adding our first layer here. So our first layer is a conv2d. That's what we call it. And now we have open brackets here, and we have some parameters to fill out. So let's go through these parameters. First one is a number 32, then the kernel size we can see here, then the type of activation we use, and input shape being equal to input shape. That's a bit confusing. I'll explain that to you shortly. So let's go through each one. First one here, 32, that specifying firstly the number of kernels or filters. So in our first layer, we're using 32 filters of kernel size 3 by 3 with an activation function using relu, and our input shape is equal to input shape, and that's because previously above this code we created an input shape parameter, or variable I should say, that was 28 by 28 by 1. That's our input shape we use. So I just left it out here for convenience because we tend to leave it out and just have it defined outside of the scope of this declaration here. Now to add another layer, it's as simple as model.add. Keras is so easy to use. You just keep using model.add, and it stacks these layers on top of each other, starting with the first to the bottom layers. So now we add another convolutional layer, 64 filters this time, same kernel size, and note we don't need to specify kernel size every time we do it. It knows that the second parameter is kernel size, so it's 3 by 3, and again, activation, relu. And now, you've noticed, we don't need to specify an input shape here. And do you know why? That's because this layer is directly connected to this layer. So it takes the output of this layer, and it knows the output, so the output of this layer is effectively the input into this layer. So we no longer have to declare inputs anymore. So now, you can add a max pooling, and I said before we're going to use a max pooling of 2 by 2. So that's simple here. We have model.add, max pooling 2D, and specify the pool size. Open brackets 2 by 2, close brackets for this here, close brackets for this here. And then we do a flatten. I haven't discussed flatten. Flatten is an actual layer. It's basically a function we do that we use to feed the dense layer or the fully connected layer. You'll see it visually in the next diagram on the following slide. Basically, we then add a dense layer here with 128 units, all being activated by relu. And this is connected to another dense layer here, which outputs the number of classes. So classes in this dataset here were 10, because we're using the MNIST dataset, 0 to 9. And we use the softmax activation to get basically the probabilities. So I hope you think this is quite simple, because to me this is quite basic. You may take a little while just to get familiar with how these things work, but you'll get used to it in this course, I guarantee it. So let's take a look at what we've built here. Okay, so this is actually what we have built so far. So we have our input image here, 28 by 28 by 1, 1 because it's grayscale. If it was a color image, or RGB image, it would be 3 depth here. So as you saw before, we have 32 filters here, connected to another conv layer with 64 filters here. And you may have noticed the size of the image shrank here. It became 26 by 26 and then 24 by 24. And that's because we didn't use any zero padding. And I'll show you guys later on in the code how to do zero padding. It's quite simple. But for now, just remember, when you don't use zero padding, our input image, our convolutional feature map size reduces from the input image size. So we have these two conv layers stacked here. Then we have our max pooling, which basically shrinks this by half. I have a dropout thing here, but we didn't actually use dropout before in the code. But in the actual code, when we start our project, I'll show you quickly how to actually implement dropout. It's one line, super easy. What I wanted to show you though was we have the flattened layer here. Now the flattened layer, if you go back to it here, was just flattened in brackets. And what does that actually do? Flatten basically takes this multi-dimensional matrix, 64 by 12 by 12, and basically turns it into a row of 9,216 columns. So what this means here is that we just flattened this matrix. So instead of having 12 by 12 by 64. Imagine you just built an entire long row where it's the first 12 here, then second 12, and then it's just consecutive long, basically a long row. And that becomes this output box here. And now this output box here is fed into the fully connected layer here with 128 nodes. Let's go back to it here. So we defined it here, and each node is connected to a ReLU activation unit. And then finally, we connect this to our final dense layer with a softmax activation function, and it outputs to 10 nodes. 10 nodes because our MNIST dataset has 10 classes. So that's how we get our probabilities here. So it's not illustrated here, but later on you will see it. So now that we've built our model, we are ready to compile this model. So compiling simply creates an object that stores our model we've just created. And we can specify our loss algorithm, our optimizer, define our performance metric that we want to look at. And additionally, we can specify parameters for the optimizer, such as learning rates and momentum. So this is a simple modeler compile code here. We have our categorical cross entropy defined as a loss type. We have our optimizer, SGD, being stochastic gradient descent. And we have our metrics to look at being defined as accuracy. So how do we fit or train our model now? So following a simple, basically what sklearn, which is the most established and popular machine learning library on Python prior to TensorFlow and Keras. Basically they just applied model.fit, where they use the training data, the training labels, xtrain and ytrain. That's what they are. You'll see them referred to in the code soon. Specify a number of epochs and the batch size. Now the batch size, this doesn't impact your learning that much significantly. However, you basically should use the largest batch size as possible that your memory allows. So you can experiment and try it. You will note if you try a too large a batch size, your kernel will crash. So generally I tend to not avoid having my kernel IPython notebook crash. So I'll use basically a batch size of 32 for pretty much small images or 16 for larger images. And once we do that, we can now evaluate and generate predictions afterward. So by running model.evaluate and feeding it the xtest and ytest labels with a batch size, we can get these metrics here, this metrics parameter, this metrics object. And then we can use that to actually look at different graphs and different interesting performance information from our model. And if we wanted to ever predict an individual point, like you have an image and you want to get the actual class it belongs to, you can use model.predict. Model.predict allows us to feed one image at a time, or you can feed the entire data set here as well. So that's it. So now let's get started to build our own MNIST handwritten digit classifier. Hi, and welcome to chapter 8.2. We are now about ready to start building our handwriting recognition CNN in Keras. But before we actually dive into the code, let's actually talk about how we approach this problem and what the problem actually is. It's a very good practice in data science to actually think about your problem, think about your data set, know a bit about your data set first before trying anything crazy and training a model on your data. So we're going to use the MNIST. This is a famous data set. Basically, it comprises of 60,000 images with 10,000 test images. And 60,000 images are comprised basically of 10 classes. So you have like thousands of like zeros, ones, twos, all of them here in this training data set. And you can read more about it here. You can click these links afterward. Basically, this is the guy, Jan LeCun. Basically, he was a guy who trained LeNet, I believe. And that was basically the famous CNN. It actually scored 99% accuracy on the MNIST dataset. It's quite interesting. So the problem. Let's look at the origin of the MNIST dataset. It was developed by the US Postal Service because they needed a way to automatically read postcodes, handwritten postcodes on mail. So the aim of our classifier now is to take these digits and basically build a model that will tell us this is a 5, 6, 2, 7, 4, and 8. And this is the CNN. Remember we had outlined the CNN before, and I showed you how to build it in Keras. We're actually now about to build the CNN in Keras. So it's going to be quite exciting. So let's move on to our IPython notebook. Okay, so before we actually dive into our notebook, I'm just going to talk a bit about loading our data. So Keras has some built-in data loaders that are quite easy to use. However, we still have to do some manipulation to our data afterward, and we'll get into that shortly. But let me just show you quickly what this is. So from keras.datasets, we import MNIST. There are a few datasets Keras can automatically import. MNIST is one of them, and Safari 10 is the other. So this is how the dataset from the load function comes out in this form, and we can define these variables as any names we want. However, this is a standard naming convention I like to use. I realize that Francois Cholet actually uses these same variables names as well, and in a lot of tutorials you'll see sometimes slightly different naming conventions, but generally xtrain and xtest are basically the training data and our test data, and ytrain, y refers to the class labels. So we have ytrain tied to xtrain. This is going to be the same length. So if this is like 60,000, this will be 60,000. And if this is 10,000, this will be 10,000. 10,000 like records, I mean. This is obviously an image here and an image here. So it's going to be slightly different shape. So we can actually print a shape here, xtrain.shape, and it gives you this output here. So it tells you that we have 60,000 images, and each image is of 28 by 28 dimensions. So let's do this now in our IPython notebook. Alright, so this is our IPython notebook here, 8.3 to 8.10. It's in one notebook. It's in our same deep learning folder you've seen before. So this is the code I just showed you in the previous slide. So let's just go ahead and run this code by pressing Shift Enter. And it takes a little while to load. If you don't have the data saved on your machine, you'll see it downloading. Some download bars come up here below. So we just printed the shape for ytrain. Let's take a look at xtrain. Xtrain is what we saw in the previous slide, 60,000 by 28 by 28. And let's see what ytrain looks like. I think we just looked at it, 60,000. Let's see what xtest looks like, 10,000 by 28 by 28. And this, we assume, it's going to be 10,000. Good. So I just did it here, but initially we can always do it here. So in this step 2a, we examine the size and image dimensions. It's not required, but it's a good practice, just to check and make sure all your data is correct. So we know our data consists of 60,000 samples of training data and 10,000 of test data. And our labels are appropriately sized, so we actually should check this here. Appropriately sized meaning that they're in the correct format that Keras requires. And as I mentioned before, they're 28 by 28, and there's no third dimension or fourth dimension if you want to consider this being the first dimension here, this meaning the number of images stored here. So let's take a look at what happens when we run this code. It prints out this here, which is the shape we saw before, how many samples in our training data, how many labels are in our training data, how many samples in our test data, and samples and labels in our test data here as well. So these all match up, that's good. And the dimensions here are 28 by 28, 28 by 28, so everything is all good. You can take a look at this code and try to understand it if you want to. It's quite basic and simple. Basically we use, these are all NumPy arrays when it's loaded into it here. And basically we can use the .shape function, which is an extremely useful function to just get a shape, basically the dimensions of your data array. So now, let's visualize some of this information. So I'm going to do this in two different ways, okay? I'm going to do this with OpenCV, then I'm going to do this with Matplotlib. And you can use either one going forward. I tend to use Matplotlib if I'm plotting multiple images on the IPython notebook, and OpenCV if I'm testing and wanting to display text over an image. So let's try this. Oh, there we go. It pops up in the window here. So we took a look at it's a 9 again, 3, 2, 0, 1. So we just brought up all these windows here and all of these digits. These are random digits. We use this function, nprandom, and this defines any random number between 0 and the whole length of our training data. The length of our training data, if you remember, was 60,000. So this generates a number from 0 to 60,000 and displays the image here using our OpenCV functions. So let's now do the same with Matplotlib. This is the code to basically plot it in Matplotlib. This is not the actual most efficient way to do it. The most efficient way would be doing it into a loop, but I just left it here for you so you get an idea of how we use subplots to plot it. So let's do it. this is good. X-train is not defined, and that's because this one may have changed it before, but let's run it again. There's another X-train right here. There we go. So I've just plotted 6 images in a nice small grid here. So this is why I said I use matplotlib to display images in the IPython notebook. I find it easier and nicer to work with. So that's how we basically import our dataset and visualize some data from our dataset. Next, we're going to prepare our dataset for training. So let's take a look at that shortly. Right, so we've just imported the data into Keras. However, that data is not in the ideal or the correct format that Keras needs to train on. So this chapter is going to be a tiny chapter on how to get this data into the correct shape. So let's look at the next slide. So as I said before, we've brought this in here and imported it here. All right. However, Keras requires it to be in a special shape, and that shape basically is number of rows, columns, number of samples, rows, columns, and depth. So this is how Xtrain looks here, but how Keras actually wants it is 60,000, 28, 28, and 1. So we sort of have to add a 4-dimension onto our data, and that's how we do it here. So now let's do this in our. And the reason Keras is looking for 4-dimension here is because when you load a grayscale image dataset, it doesn't add the dimension of the depth, the color depth, mainly because it's a grayscale and there's no color depth. If it was a color image dataset, you would have the tree popping up at the end here. However, we need to add this 1 just to indicate to Keras that it's a grayscale image dataset. Otherwise, it's going to return an error saying it's in an incorrect format. So to change this, you just use NumPy's reshape function, which is quite simple to use. You just use xtrain.reshape, take the first 60,000 digits here. That's when you use xshape. This is the first dimension at 0 addresses. Then you enter 28, 28, or image rows, image columns, and add the 1. And it's quite simple to use. So let's return to our IPython notebook now. Okay, so like we just saw, this is a section of code where we reshape and add the 4-dimension onto these training datasets and test datasets. I didn't point this out to you before, but we just get image rows and image columns by simply just addressing the first dimension of the shape here. Xtrain. Now we use Xtrain 0 and Xtrain 1. We don't need to use Xtrain. We can use Xtest as well because they're the same dimensionality. However, this just gives us the rows and columns. So let's actually print this out so you can actually see what's going on here. So let's run print that. You'll see it returns 28. So this is getting the 28 here. And if we were to just use this for columns too, you'll see we'll also get 28. All right, so moving on, this is fairly simple for you guys. Let's make our code nice and neat again. This is how we make the input shape. Now you've seen before we needed the input shape dimension in the first layer of the convolutional neural net. And this is how we just create our image shape here. It's a tuple that's combined with rows, columns, and the dimensionality of the depth of the image. This would be tree again if it was a color image dataset. And because Keras expects data to be in a float32, right now I believe it's going to be in some sort of integer format here. So we just need to change this. So we just change xtrain as type float32 and do it for xtest as well. We don't need to do this for the labels, just the training data. And this is how we normalize our data. We normalize our data by dividing it by 255, because remember our images range from 0 to 255. So if we divide our image data by 255, we basically bring it into range 0 to 1. So that's quite simple here now. And basically we just print this out again. You don't need to do this because we did it before, but just to do a sanity check on our data. So let's run this again. If you want to see what xtrain actually looks like now, this is it. You can't see basically the decimal points because it's kind of hidden here, but all the data ranges from 0 to 256, to even 0 to 1 right now. Okay, so let's move on to hot encoding our labels. Hi guys, and welcome to chapter 8.5 where we talk about hot one encoding. So as we saw before, we did some transformations on the xtrain and xtest data. That's our image data. Now what about our label data? That's ytrain and ytest. Well, let's find out. So let's recap what we did on the image data. We added a 4th dimension to go from this to this. We changed it to float32 data type, and we normalized it between 0 and 1 by dividing by 255. But what do we do to the label data now? Let's check. So the label data is basically in this form. For Y-train, it's going to be a matrix that is 60,000, that has 60,000 elements, and each element indicates a class label. So for Y-train, which is a 28, the first element in X-train is going to be 28 by 28, and this 0 corresponds to its label here. However, Keras does not use label data like this. It needs it to be hot1 encoded. And what does that look like? That looks like this. So we have labels here, and instead of having a 4 being represented here, it's basically a matrix that has 10 columns now. So instead of having no columns, so effectively one column, sorry, 60,000 columns, it has 10 columns here and 60,000 rows. And each column, each row, sorry, has basically a 1 or a 0 indicating which label it is. So imagine we have this being transformed. Sorry, let's look at this. This is the 3rd row here being transformed into this. So instead of having this row be 4, hot1 encoding makes it into this. I hope you understand clearly. So we're going to do this now in our IPython notebook. Okay, so step 3b is the hot1 encoding of our Y labels. And to do this, we basically use NP utilities that are imported from Keras utilities. And all this does here, it just sends it to categorical. That is how Keras calls this function, hot1 encoding, to categorical. So we have ytrain is equal to np utilities dot to categorical, and you just put the ytrain here, and that transforms it. So let's take a look at how this actually looks. So let's run this here. So now ytrain, let's look at the first row in ytrain. It's this. And basically you can see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 elements. And with this one, this looks like the 9, 8, 7, 5th element here. So this is number 5. So the first element in our training data is number 5. So now let's move on to creating our model here. So now we move on to a simple step where we actually build and compile our model in Keras. And this is the model we're going to build. As you remembered, we have shown you this before, how you actually add layers, how we actually do max pooling, flatten, dense classes and stuff. This is actually quite a little useful diagram I created that shows you how to basically layer and add each piece here, including dropout and including our flattened layer here as well. So let's go ahead in Keras and run this and compile our model. Okay, so welcome back to our IPython notebook. So I'm pretty sure this code looks familiar because you would have seen it in the presentation slides earlier. So remember I said we're building a simple convolutional neural net? This is how we do it. We have 32 filters in our conv layer, kernel size 3 by 3, activation ReLU. We have the input shape, which we defined above here. Actually, it was in this block right here. And then moving on, we have another convolutional layer with the same kernel size, same activation. We have the max pooling downsampling layer. We now use dropout, and dropout is simple to implement. You just model add dropout and specify p. We use p as 0.25 here. We then flatten this layer, have a fully connected dense layer with 128 nodes with ReLU. We add another layer of dropout, and we have a higher dropout here. Note you can play with these values and see what gives you the best. You tend to start with dropout smaller on top and get larger, but you don't ever really go larger than 0.5. And then this is our last dense layer, which is connected to 10 nodes, which is our number of classes. And our number of classes was defined right here. That's basically the length, number of columns, I should say, in this array. And that's it. So I talked about compiling a model. Now, when we do model.compile, basically we're taking these layers, creating a model, and then specifying what type of loss we're using, what type of optimizer we're using, and the metrics we need to look at. And these metrics we need to look at are basically the metrics that will be output when we started to train our model, when we start training our model. And by doing model print here, we can print the model summary and take a look. So let's check it out. This is very cool here. Let's go through this quickly. So when we print a model, we actually see each layer we have. This is each layer we specified above here. And what's cool about this is that it gives you the output shape. So we know the input shape coming into this here. The input shape was 28 by 28 and dimensionality 1. And we have 32 filters here. So our output shape, if you remember correctly, is going to be 26, 26, 32, with 32 being number of filters. And these are the number of parameters in this layer here. So this is pretty cool. So now we have second convolution layer here. Same thing again, but now a lot more parameters going forward. We have our max pooling here, which is just process, no parameters. Drop out again, flatten again, and flatten has an output shape of this, as you can see. It's just this expanded into this. We have our fully connected dense layer here, and this is where the bulk of our parameters actually exist. And we have drop out again, and then our fully dense connected to the 10 classes here. So this gives us our total number of parameters, total number of trainable parameters. We have 0 non-trainable parameters, and we will come to what non-trainable parameters are later on. And so we're now ready to train our model. So let's get to it. Okay, so welcome to 8.7, where we start training our classifier. So let's return to our IPython notebook now and get started at actually in doing some training. Okay, so welcome back to our IPython notebook, where we're going to start training our model. So let's go through this line by line, alright? So remember batch size, which is basically how many images we process in one batch. Effectively, this depends on how much RAM or VRAM you have available. Because MNIST is a small data set, you can probably even get away with going up to 128. However, let's put it at 32 to be safe, in case you have lower specs on your system. For epochs, usually we can use 10 or 25 even, but for this demo, let's just use 1 so you can actually see it run and actually see what happens at the end. So now let's talk about model.fit, and you have something called history equal model.fit. Now ignore history for a second. The key part here is model.fit. You don't actually need this history stuff here. This history is mainly needed to plot our graphs afterward. But for now, you can train a model without doing this. You can simply run this line and it trains. So let's look at what inputs we need into model.fit. We need the training data. We need the training labels in the format we specified above. We need to specify our batch size, which is 32. Epochs, which would be 1. Verbose, basically that just tells us how much information we want to see while we're training. I recommend verbose 1 because it's nice to look at and provides a lot of information. And lastly, the validation data, which would be X test and Y test. And this is also paired in a tuple. As you can see, these brackets basically ensure it's a tuple. And that's what we fit our model on. And lastly, let's take a look at this line. This is where we get our evaluation metrics at the end of our training. Evaluate basically just gives us a score at the end, a loss score, and accuracy score. So let's now run this and visualize how training is done. Amazing. So now, I find this quite interesting to watch, but you may be bored. But right now, this is basically going through the images here. How many images are we have trained so far in this data set? The estimated time to completion, 2.5 minutes left. Our loss, and you can see it continuously going down slowly. Actually, this is pretty fast, to be fair. And our accuracy. This is a part I like to watch too as well. Our accuracy is slowly going up the more and more data we feed our model. And this is on 1 epoch, and we're already at 60% accuracy. So if you wait this out, I'm going to fast forward the video while we watch this. You can actually see after 1 epoch, we actually reach quite good validation and training accuracy. However, you don't see the validation accuracy and validation loss just yet, because right now what's happening is that we're passing our data set, our training data set, to our model and back propagating it and updating the weights. And that is how these things are improving. Loss is going down, accuracy going up. And once 1 epoch is complete, then we pass our test data into it, and then we see our validation loss or test loss, and our validation accuracy or test accuracy. So let's wait until it's done. Okay, good. There we go. We're finished. So now let's look at the results here and try to figure out how we analyze what had just happened. So as you can see, after we fed all 60,000 images into our model and trained it, updated the weights, we now have a loss that is decently low, 0.59. We have our accuracy on our training data set that's at 0.8145, that's 81.5% roughly. But interestingly, our validation loss is even much lower than our training loss. And our validation accuracy is 93%. Now that's not normal, but it's a good problem to have. It means that our model has generalized very well and is actually quite accurate on our test data. Now this doesn't always happen. Usually you'll always, or in most cases, have a higher accuracy in training than on the validation set. However, we wouldn't complain about this. This is a good problem to have. And basically we have our loss and test accuracy printed at the summary here. It's also the same values here, but we just run this again just to basically see it at the end. If you have many epochs as well, this is a summary at the end of the model. Okay, so now we're going to move on to plotting our loss and accuracy charts. Basically what you should do is run this for maybe 10 epochs so you can actually have nice graphs. Okay, so now that we've trained our model for maybe at least 10 epochs, we can start plotting our loss and accuracy charts. And I don't know if you remember those charts correctly, but let me show you what they looked like in our previous slides before. This is an example, this is not real data, of overfitting on our charts. So as you can see, this was basically, we got very bad test loss and test accuracy, but really good training accuracy and very low training loss. Okay. So let's see how we actually plot these graphs in our own IPython notebook. Okay, so here we have the training output of 10 epochs. As you can see, it starts at 1, goes all the way to 10. And as you can see, the training accuracy starts at 91, then gets better and better. And look at the evaluation accuracy. It's basically a little hard to see because it's all the way here. But it starts at 95, and then 97, 97.8, keep going up and up to reach 98, 98.6. So that's pretty good, but it would be nice if we had all of these data on a graph, wouldn't it? So this code is pretty simple matplotlib code. We'll actually go ahead and process these plots for you. So let's print them. This one is our loss chart. So this is pretty nice. We can see our validation and test loss here. Starts at somewhere high, 0.14 roughly, and goes down all the way to maybe 0.3 or 0.04 actually, sorry. And there's a training loss here, so you can see this as well. So it's very nice visuals, and when you want to just see if things are overfitting as well, you can actually start seeing things like the training loss, the training accuracy basically getting higher, but validation loss or validation accuracy getting lower or worse. So let's look at the accuracy plots now. This one plots the accuracy here, and basically actually I mentioned before how we equate the model stuff to history here. History basically allows us to store this data here. So then we can actually refer to get our history. So history.history creates a history dictionary, and then we just get a loss from this dictionary, get a validation loss as well, and we just equate them here. And this gives us an array of those values, and then we can plot them here and tweak things like line markers, line size, and we do the same for this here. We actually, instead of getting loss, we get accuracy now. And as you can see, this is a nice chart. Always good to see both of these things going up and up. What's good about this, at least not always, this doesn't always happen, but what's good is that validation accuracy is higher than training accuracy. So that means it's generalizing quite well. So you want to see these both move in the right direction. You don't want to see the blue peak and then come down, and you don't want to see this going up and up while that happens, because that means it's overfitting. Okay, so let's talk about how we save our models that we just trained. We spent some time training a model, and we don't want to lose this model when we close our IPython notebook. So let's figure out how we save and load our models. Okay, so we just spent so much time training our model, so let's get to saving it now. So if you scroll down below these charts here, the code to save is actually quite simple. It actually is part of the model object, and you just specify the directory and file name that you want. So basically we can just call this chapter 8, which is from 8 here, mnis simple CNN 10 epochs. You can actually put an underscore here, make it look a little bit nicer, and voila, it's saved instantly. So now, if we want to reload our model, let's just enter a new file name here. And we use Keris's load model, which is part of the models library here. And this is what's strange to most people. Loading isn't as instantaneous as saving. And that's because it has to actually unpack everything now and put it back into the model format. It's a bit tricky to understand. I actually spent some time trying to figure it out because I had a project where I was loading 50 different models at once, and it was taking maybe about 5-10 minutes to load all of them together. So let's just run this quickly. And there we go. This took about 5-10 seconds. And so now our model